Topic 6.3 work. Now here consider a constant force acting on this object. Mass of this object is m. Okay, consider a constant force acting on mass m object. Displacement of this object is d in x direction. In x direction. So work is equal to F into d. Work is equal to F into d. Means in this case, suppose direction of the force is create a theta angle. So in this case, F cos theta into d. F cos theta into d means F into d. Now, no work is done if in first case, suppose in this case, displacement is 0. Displacement is equal to 0, so F into d 0, so 0 work is equal to 0 in this case. Okay. First one is displacement is equal to 0, so work is equal to 0. A weightlifter holding a 150 kg steadily on his shoulder for 30 seconds. Time is 30 seconds. So here no displacement. So no displacement. So d is equal to 0. So work is equal to 0. Now in the second case, F is equal to 0. Now in second case, F is equal to 0. One block moving smoothly. Means friction force is equal to 0. Friction is equal to 0. So in this case, work is equal to 0. So F into this one portion 0. So W is equal to 0. Okay. First one is D is equal to 0. So work is equal to 0. Second, F is equal to 0 means for smooth surface, friction is equal to 0. Friction force is equal to 0. So in this case, again W is equal to 0. Now next, last one case is angle between displacement and force is perpendicular to the direction. Angle between force and displacement perpendicular to the direction. So cos theta pi by 2. Cos pi by 2. Cos pi by 2. Now here we know that cos pi by 2 is equal to 0. So again in third case, work is equal to 0. Again W work is equal to 0. Now work can be done in both case positive and negative. Now if theta is equal to between 0 to 90 degree, between 0 to 90 degrees, so cos theta is positive. Now if theta is equal to 90 to 1 degree, so what theta is, cos theta is equal to this in portion negative. Okay. Now work and energy same dimension. Dimensional formula for M1 L2 P minus 2 for work. Here we know that F into D, force M1 L1 P minus 2 into D. So this one M1 L2 and P minus 2 for work W. Unit of this SI unit of work is joule. Second one is Newton into meter. SI unit of 6.4 kinetic energy. Now here if a object of mass m has a velocity v, so kinetic energy of E is equal to 1 by 2 mv into v means is equal to 1 by 2 mv square. This is the mass of object, velocity of object. So kinetic energy K is equal to 1 by 2 mv square measured in work. Next topic 6.5, work done by a variable force. Work done by a variable force. So first here consider a small part of displacement, means small part of displacement at this situation. The force f of x and displacement in this case is del x, so work done is equal to del w. Okay, so now here first we calculate this small portion of work done, means small displacement in this particular area. Displacement is small, so approximate constant and work done is del w is equal to f of x into del x. Okay, now so in this case from initial to end point of the small portion, this is here we take summation, means total work done by, in this case total work done w is equal to summation xi to xf into f of x into f of x del x. Now first again I repeat, for small displacement applied to the force, so force into displacement is equal to what? Force into displacement means is equal to what? So now here in this case, first one is here we calculate this small work done for this small displacement. Now second, in this total portion of the displacement, so total work w is equal to summation xi to xf f of x into del x whole portion of the case. Now the number of the term in the equation, next figure in the figure number is 6.b. This is the small. Now next portion for the smooth area in this particular area, work done total, this one is first initial and this is the end of the point. End of the point, next figure is 6.3. Figure 6.3. So in this case w is equal to limit del x tends to 0, limit del x tends to 0, summation xi xf f of x into del x into del x. So is equal to integration of xi and x of x f of x into dx for the figure number 6.3. In this case work done by a variable force. Okay, now next point 6.6, work energy theorem for a variable force. Work energy theorem for a variable force. Here we are now familiar with the work and kinetic energy for a variable force. So now in the one dimensional, the time rate of change of kinetic energy is here dk into dt, means is equal to d upon dt. K is equal to 1 by 2 mv square. Okay, K is equal to 1 by mv square. Now here 1 by 2 and m is value. So in depreciation of this portion means 1 by 2 m constants d upon dt into v square. Okay, d upon dt into, in this case, v square. So here in this case depreciation of v square is here, depreciation of v square 2v. Okay, so 1 by 2 1 by 2 into 2v into dv upon dt. Again depreciation of only v. Okay, first depreciation of in this, so 2v, so this one cut. So here m into dv upon dt, m into dv upon dt and v. Okay, so now here in the case from the Newton's second law, dv upon dt is equal to, we know that a means ma is equal to f into v. Okay, ma means f and this one is v, so f into v. Okay, so dk upon dt is equal to f into v. Okay, so now dk is equal to f, in this case from the dt to, in this case, dx, small portion. So integration from the position of initial to final means xi and xf. So now kinetic energy initial to final, in this case initial and final. Okay, so now final kinetic energy minus initial kinetic energy is equal to, final kinetic energy minus initial kinetic energy is equal to W, is equal to W. So this is the work energy theorem. Kf minus Ki is equal to W, work energy theorem for a variable force, for a variable force. Okay.